It is now 26 past the hour, and I am excited to see that the table is slowly filling in and that we're getting some results. Crowdsourcing in progress.
Yeah, so I would suggest that we keep this running. Do you want to continue with your presentation, and everybody who has a run completed just fills the corresponding number in? Should we do it that way?
Yes, I think that's a good idea. I don't have too much left here, or we don't have too much left in this tutorial. But we want to cover a few more things that are important, that you should know as an aspect beginner, and things you need to keep in mind for the rest of the week for the tutorials. But yeah, so please continue to fill out these the form. Okay, let me share my screen. And okay, so I have to figure out how to do full screen. Okay, so this is the last section that we want to present here to you about how to get started using Aspect. And you already know how to modify a PRM file, run it, to look at the output, and to get information out of it, for example, regarding statistics. There's an important feature in Aspect, namely you can run Aspect in debug mode and you can run it in optimized mode. And you might have noticed, especially those of you who have just run something which with a finer refinement level than the first example, you will notice that it takes a lot longer. And the good news is if you run in optimized mode, it will run a lot faster. It will also run faster by running it in parallel, which I will talk in a second. It will also run faster if you don't run it in a virtual machine, but on a more powerful computer outside a virtual machine. But anyways, the most important thing that you absolutely need to know is that there's a debug mode and there's a release mode or optimized mode. And the debug mode is slow, very slow. And well, why, you might ask? It is because we run a lot of checks to verify that whatever you are doing is correct. So very helpful error messages come up if something is wrong in our mind. And the problem is that this is too expensive to do all these checks for a very serious and large computation, especially in 3D. And so we provide the option to compile in debug mode or in optimized mode. And in debug mode, you get all these checks that tell you when something is wrong or incorrect. And the second thing is that we disable compiler optimizations. So the code is run. That's also where the name debug build and optimized or release build comes from. This build does not optimize away functions and inlines them and makes the code in effect much slower than it could be. And the reason to do this is that debugging is much simpler. So if you ever run a debugger with C or C++ code, where you can step line by line into the code to see what is happening, that doesn't really work if you turn on compiler optimizations, because the function call that you think should be there is actually not there. But I would like to stress how helpful the debug mode is for developing and finding mistakes. So the opposite of the debug mode is the release mode. And there, most internal checks are switched off, and we try to optimize the code as much as possible by giving the compiler the freedom to optimize. And in effect, this means that running in release mode can be in order of magnitude faster. And the default is debug mode. Before I continue, let me quickly show you the virtual machine. And this is where I left off. So let me open up the terminal again. And you might remember that if I run Aspect without any parameters, it shows me this header, right? It shows me this helpful information text and tells me, yeah, you should be running with a parameter file. But what it also says is in this header here, you can see running in debug mode. This is not clearly, my highlight is not really clearly visible. I hope you can see the cursor. So there's the 6th or 7th line from the top says running in debug mode. Also, when you look at the output, right, if you look at the log.txt, there also debug mode appears and shows up. And when you run in optimized mode, it will show release mode there. So this is important, right? And yeah, so the executable that you have here is in debug mode. Okay, so debug mode helps with finding problems. Optimized mode is fast. General guidance. Always test while you develop things in debug mode. All new setups, models, plugins, whenever you modify PRM files, it's a good idea to run it in debug mode first. You will find a lot of problems. And if you don't, the first thing you should do when something crashes or doesn't work is you should switch to debug mode, run it, and see if any error messages show up. Something like an off by one error, an index that is wrong, some internal check is incorrect. For example, oh, you have a negative density somewhere that will be tracked and trapped in debug mode, but it will not be visible to you when you run it in release modes. So I always work in debug mode, and only when I submit a large job somewhere on a workstation or on a supercomputer or a cluster, then I run in optimized mode. So all the tests that I do are in debug mode. Production runs have to use the optimized mode. And it's typically the case that you do more mesh refinement, or you switch to 3D, or you run in parallel, right? And never do any parallel large-scale production runs in debug mode. That's a waste of CPU time. It's a waste of heats up our universe. And you can think about the cost of a CPU hour that you would pay, for example, if you run it somewhere in the cloud or on a supercomputer. I don't know if this number is correct or not, but just think about that a CPU hour costs dollars, right? And you shouldn't waste CPU time. So whenever I see more than 2 MPI parallel ranks, and it's in debug mode, then I know somebody is doing something wrong. So that's the general general advice that I would like to do. Anything that runs longer than an hour should be run in optimized mode, unless you're trying to find a bug. So what I often have is I have something in optimized mode that breaks, and then I simplify it and run it in debug mode to see if I made a mistake or not, and then I try to find out what the problem is. And that's the typical workflow that all of us do. Even those of us who are very experienced in setting up models and running are doing it that way. And you often end up in a trap where something is broken and you should switch back to debug mode. Okay, the virtual machine does not contain a release mode or an optimized mode at this point. Later this week, you will need this. And I will show you these also in a second to run these, but these are the instructions to configure a build of Aspect in a new directory that is in release mode, and then we compile it, and at the end we have 2 binaries of Aspect. We have the debug build and we have the release build, and then you can switch back and forth. So for example, we will have later this week problems that would run too slowly, or even if you look at this tutorial example, if you do 5 refinement levels, it might take 5 or 10 minutes, but it doesn't have to if you run it in release mode. So these are the instructions, and Renee will cover this also tomorrow, but if you wanted to go ahead and already compile like this, you may do so, because it can take time, especially if your computer is slow, or if you had trouble running stuff for a long time. We don't ship this with it because it would make the virtual machine bigger. And you can also verify this if you want to do something between today and tomorrow. You can run the tutorial with the debug and with the release build and compare how much faster it runs and whether the factor of 10 is correct in your example or not. I will quickly, I'm not hiding right now, but I will quickly show you how to do this because we have a little bit more time. So if I go back to the home directory, or if I would open up a new terminal, I would be in my home directory. And you notice there's the folder Aspect. So if I go into Aspect, you will see this is Aspect version 2.2, right? And you'll see that there's a build directory in there. This build directory I already made, and it's shipped with the virtual machine. And inside this build directory is the debug build of Aspect. So I can actually go in there, and you'll see that there's a lot of, actually there's the Aspect binary in there. So I can run /aspect, and you'll see that this is indeed the same version that we have been running, right, with the debug mode. So what I'm going to do is I'm going to create a second build directory. So I do make dir build release, for example, if that's what it's called in the instructions. Then I go into that directory, and I will double check how the instructions look like, that I don't do anything different. Okay, so to set up a new build directory, you use a command that is called cmake. And what we want to do here is say that we want a release mode. And this is cmake build type release. And the last argument to cmake, and it doesn't matter if you have a space after the -d or not, is the directory where the source code is. And the source code is in the directory one-up. So I could write it as .. or I can write it as /aspect. And here it is in the slides, it's written as /aspect. And if I do this, then it's going to say, I am configuring Aspect, right? And it scrolls by. This is the DL2 version. Here's the compiler that we're using, all kinds of information. And it will run a test that compiles something, test executable. So that is, takes a second. But after that, it says here also the build type, that this is a release build. And now I can start compiling it. I'm not going to do this, but you can do this if you want. I would like to highlight one more thing. If you look in this directory that is now filled, right? This was empty a second ago. There's a file called detailed.log. And I'm going to open this file up. This is also exists in the debug build directory. Here you can see all the configurations that we have, right? And so let me try to find the release build. So here's the cmake build type, but you find a lot of other information. So for example, later this week, Menno will talk about the world builder that's mentioned here. And there's other options, for example, the DL2 version. And this is a very helpful file to know how things are configured, and it's helpful for us if you have problems at some point. Anyways, so I can compile with make now, and that takes a long time. This will compile with one processor, and depending on how many cores you have in your virtual machine and how much RAM you have, you need to compile. And so the example here is make -J2. So I can do this, but I can also just type make. This will take an hour or so. So after you're done today, you can start compiling like this, and then tomorrow you have a release build. And then running it works by just specifying the different executable. I'm not going to do this right now, but just so you know, if you want to play with it.
Timo, can I interrupt you for a second?
Certainly.
If you run into any problems during this process, then don't worry. We will go through all of this tomorrow together. It is slightly advantageous if you already have a version working if your laptop is very slow. But if you run into any problems there, we will talk about that tomorrow.
Okay, thanks. Yeah, but this is an important enough topic that it should be covered in the first introduction when you run Aspect to know the difference between a debug and a release build. Okay. The last thing that I already hinted at a minute ago, but that we haven't really talked about, is that Aspect is a parallel code. And what happens is that we use MPI to be able to run with multiple processes, either on a single machine. So for example, my laptop has 4 cores, and I also set up my virtual machine to have 4 cores, I think, or it was 2, I don't know, I can check in a second. Then I can run a simulation that uses 2 processes, or 4 processes, or however many I have in my workstation. And we also use MPI to run in parallel on a supercomputer. So there are situations where you want to run on 1,000 cores. So then you would do MPI run with 1,000. And we regularly do these kind of things for large and complicated models that would otherwise run a long time. You can also try this in the virtual machine. It's not very useful to do it in this virtual machine, but it works. And remember that you ran aspect typing ~aspect/aspect tutorial.prm. And if you put in front of it MPI run -np2, this will run with 2 processes, obviously. And I'm going to quickly show you that as well, just because I have the virtual machine. And so you can see here that I'm compiling very, very slowly. I'm at 3%. So anyways, I'm aborting this for now because I want to show you the example, right? So remember that we had the day 1 with the tutorial PRM. And if I look again at the, let me use leafpad output log txt, you remember I ran it and it ran for 22 seconds. And I'm going to run it again, but this time I'm going to run it with -np2. And the name of the file was tutorial PRM. So it is MPI run -np2 aspect tutorial PRM. And I'm going to run it, and I'm going to not be able to see anything because it's running by too quickly. And you might wonder if it actually gets faster or not. And I don't know, I haven't tried it out. I assume it's not getting much faster, and we get to Y in a second. But maybe it is a little bit faster. So this is 16 seconds. Remember a minute ago, it was 22 seconds. So it's not twice as fast. I'll explain to you in a second, but it is faster, right? And the other thing that might be worth pointing out is if I open up the new log txt, you will see at the top here that we are indeed running with 2 MPI processes. Before it was saying 1 MPI process. And also note that I'm still running in debug mode. Okay, so this is how you run, and let me show again what the command was. The command was MPI run -np2, name of the executable, name of the PRM file. Okay. And I can run with more than 2, obviously, but it depends on how you set up your virtual machine. And now the question is, why is it not twice as fast? And what is the correct number of cores to use? And it depends a little bit on your problem, but a good first guideline would be that you need about 30,000 unknowns of the linear systems of the total number of unknowns of your variables per processor or per process. Meaning if you have less than 30,000, it is probably not worth it at all to run in parallel. If you have 60,000 unknowns, it's probably a good idea to run with 2 processes, just about. And so on, right? So to use 1,000 cores, you actually need to have a large enough problem where this matters. And the reason is that when you run in parallel, you have an overhead because the processes need to communicate with each other. And if the problem is so small, then the processors basically don't have anything to do and they actually slow things down. And we can look at the number of unknowns in the simulation that we have. So if I open up the log txt, you will see that this example has only about 1,000 unknowns. So the linear system that we are solving for velocity and pressure in total has 1,000 unknowns because we're in 2D, and I have this example here has, I don't know if it's 2 or 3 refinement levels. So it is quite a coarse mesh. I think I have 3 here. Of course, this goes up by a factor of 4 every time you refine. So for those of you who have been running the benchmark on finer refinement levels, this number will be bigger. This is not a fixed number, but something in the order of 10 to 50,000 unknowns per process is typically a good number. And we actually have the number down here. So with 3 global refinements, we have 1,000 unknowns. With 5 global refinements, we only have 13,000 unknowns. So even then, running in parallel probably doesn't help much, if at all. Running parallel computations, scalability, parallel solvers, this is all a very complicated topic. And we spend a lot of effort in benchmarking and optimizing these things. So this is just a a very quick reference for you. And the numbers also change whether you use release mode or debug mode. And in general, if you run in parallel, you probably want to run in release mode unless you try to find a bug or unless you are just setting up your model. But so in debug mode, the 30,000 might be a little bit too high and you actually gain something if you have fewer unknowns, like I showed you in the example just. But again, there's a point where you add more processors and it not only doesn't get any faster, it actually gets slower. Okay, and this is all that we wanted to cover on the first day of this tutorial. Are there any questions about anything that I talked about right now? I will try to find the chat window.
I think we've answered most of the questions in the chat window.
Okay, so that looks very good. Let me quickly jump to the table to see how the results are shaping up. And it looks like, except one value, we have all results for 2, 3, and 4 refinements. So this has been awesome. And this is great, great to see. Well, 2 values missing maybe. The one thing that you always have to do, and I'm not sure we stress that, is to actually check whether you are at a steady state and the value is converged, right? We showed you how to plot the statistics file. And especially for the very right column, for the high Rayleigh number, we are actually not at a steady state, but the number more or less converged. But this is probably the only one, the last 2 columns are probably the only ones where we don't get to a steady state and where we're not completely converged. Anyways, let's look at the results, shall we? So this is the table here on my screen. And you can see the first observation is for 2 refinement levels, it seems like that for the high Rayleigh number, the resolution is not good enough because these are outliers, right? The other data points for the other refinement levels are rather close to each other. They're not identical. Again, the resolution matters, right? And the higher resolution is likely more accurate. If you actually look at the graphical output, you see that the plumes are under-resolved in the coarser resolutions, and you need refinement level 4 or 5 for the high Rayleigh number. For the low Rayleigh number, you see that all refinement levels are basically on top of each other. So they all agree on the heat flux of the system, even if the solutions are slightly different, as you can tell. There are some differences, but if you look at the general trend of, for example, the yellow or the green line, we pretty much track the dashed black line, which is the maybe correct relationship to expect between the Rayleigh and the Nusselt number. But this is great. This is kind of what I expected, and this is very good results. And for those of you who ran the result like this, it's very interesting to look at the output at the high Rayleigh number for different resolutions to see how that changes and how accurate that is. So thank you all for contributing your compute time and the heat to this benchmark. This has been great and worked surprisingly well.
Timo, there was an interesting question in the chat, which someone brought up about 3D scaling and then how to go about testing that. Should we wait for another day to sort of go over that or save that for a discussion? Or is that worth addressing now quickly?
Do you want to address it quickly? Maybe that makes sense.
Sure,
I think you wrote it, but, yeah.
Yes, and so then there was a question from David Quiorga, and the question was, what about speed using more nodes and processors per node? Is there an optimum combination or rule of thumb regulated 2 degrees of freedom? And so, yeah, as Timo just pointed out, in 2D, that number is about 30,000 degrees of freedom per core as the minimum value. In 3D, that goes up to somewhere between 200 to 300,000 degrees of freedom per core. And Renee or Timo or Wolfgang or anyone else, please correct me if that number is wrong. But then when you're doing scaling for large 3D problems and even 2D problems, it often depends also on other things. In this case, if in the model we've run here, if the majority of degrees of freedoms are involved in the Stokes solve, that makes determining the exact number of nodes or cores a little bit easier. If you have a lot of degrees of freedom, say, stuck in compositional fields, if you have lots of different lithologies, it complicates things a bit more. And so I guess the exact answer is for 2D, 30,000 degrees of freedom per core is a reasonable starting value. In 3D, 200 to 300,000 degrees of freedom per core is a reasonable number to start with, but then it depends very much on the exact problem you're looking at. Is that a fair summary, Timo? Or
I would add a few things to this. So ideally, obviously, you always want to use as many cores as you can for a problem so that it runs, so that the wall clock time it takes is the shortest amount of time. But the limitation is, of course, the scaling of the code. So if you spread the problem over too many cores, then the communication between the cores will take up the vast amount of the time, and you will not get any additional time. So you will lose efficiency. As John just pointed out, a common number for the scaling limit for aspect is around 30,000 degrees of freedom per core, but this varies. The bigger the problem size, the higher this number. So if you run an extremely large model, then it can happen that you need to run 100,000 degrees of freedom per core or more, as John said, 200,000. Although 200,000 is a pretty high number. I have not actually seen a model, except for the largest scaling models that we have run, that need that many degrees of freedom per core. I would say as long as you're running medium-sized models, let's say below 1,000 cores, you can safely run on something like 50,000 degrees of freedom per core. And sometimes, so these are guidelines. As John said, it depends a bit on the model setup. In particular, there is a new solver option that Timo worked a lot on with a PhD student that we will not cover in detail during this tutorial, but that allows you to go down to something like 5,000 degrees of freedom per core in the ideal case. So there's no good ideal answer here. A good way to test this is to run your model for a single time step on different numbers of CPUs and see how far the scaling goes. So if you double the number of CPUs, does the model run in half the time? If yes, then you're fine using that number of CPUs. If not, then you don't want to run the model on that number of CPUs because you're wasting the CPU time. I think that's the summary I would give to the question.
Yeah, I just want to add a little bit to this. I just posted a link in the chat. We've actually made some of these scaling tests for aspect, and they are on the CIG website. So if you happen to run on any, so first it gives you some idea of like for which size of the model, how many degrees of freedom per CPU, like what order of magnitude you would expect. And also if you happen to run a model on any of the machines we've already made tests for, that also gives you some sort of guideline for what you would want to use.
Yep. It's a hard problem to figure out exactly how to run very large simulations. Is the summary, I would guess.
Yeah.
But something in the order of 30 to 50,000 unknowns per process is probably a good starting point, and then you can play or have to play with that going from there.
I would add, it's worth spending lots of time on this. If you want to run lots of large 3D models, it is worth spending a day or two or a week very carefully testing what the optimal number of processors is. Because, for example, if you get a grant from NSF or Exceed to get computing time, you want to, optimize that as much as you can. You don't want to waste time on computations. It's valuable, and this time is worth thousands of dollars in NSF's money. So definitely spend lots of time optimizing your models first and figuring out exactly what the right scaling is. It's time well spent.
There's a question whether we have these guidelines written up, and I am not aware of guidelines for a number of unknowns written anywhere. Would we need to have? Maybe we should compile something like this.
Yes, I think the most explicitly written down form of these guidelines are the slides that Timo just showed.
Yeah,
We should probably write it down somewhere.
Agreed. Okay, I think we're at a point where we should maybe stop the conversation. Remind me exactly how the schedule looks like. Let me see. So I think we are more or less on time for the wrap up at this point, right?
Yes.
Yeah,
So
I think so too. And I mean, we're going to keep the spreadsheet open if anybody wants to try their hands with 5 refinement steps and longer computations, then we're very happy to take those results too, show them tomorrow.
So the further plan was to take a quick break, and at this time the organized activities for today will stop, and everyone who is interested in playing around with models or still have specific questions, please come back after maybe a 5 to 10 minute break. We'll figure that out soon. And then we will form discussion groups that are meant to allow you to ask questions or to play around with models. And we will try to, like, some of us will stick around and we will try to answer questions. But this is not any formal part of the tutorial anymore. So if you don't have questions, or then please feel free to leave at this point. We will reconvene tomorrow at the same time as today and continue with running some more advanced aspect models and take a quick look into how you would go about changing models if you can't find an input parameter that does what you want. So this tutorial is not about a full coding tutorial. We will not discuss the details of aspect, but we will take a quick look into how you could make simple changes. And also discuss a bit about free surface models. And start an introduction into lithosphere modeling at the end, hopefully, if we get to that. So thanks everyone for sticking around. Let's take a 10-minute break until 10 after the hour, or 40 after the hour in India. And let's see who is interested in having some smaller group discussions, and then figure out how we break this up into groups. So thanks again, everyone. Thanks, Timo and Wolfgang, for the presentations. Sure. And see you all tomorrow or later in 10 minutes.
Yes. And if you have any comments about how this first day went, and if you have suggestions for things we can improve, going faster, going slower, showing things in a different way, please let us know. You can leave comments in the chat, or you can also email us if you want to do that in private. We are, of course, very curious in what works and what doesn't work, and how we can improve, right? So yeah, if you have a minute, please let us know.